Good afternoon, good morning, wherever you are. Welcome to this webinar. My name is Srinath Sridhar. I am an industry leader at Altis Consulting. And today the title of our webinar is Time Series Data, Driving the AI Revolution. So just in terms of housekeeping, this will be a 30-minute webinar. Please do ask questions through the Q&A box, and I will pick up some of these questions at the end. I hope everybody can see and hear me okay. I'll do a acknowledgement of country. I acknowledge the traditional owners of the lands throughout Australia on which we are meeting today. I pay my respects to elders past and present, and extend my respects to all Aboriginal and Torres Strait Islander peoples today. Always was, always will be Aboriginal land. So we have an exciting agenda lined up for you. We'll talk about time series data and how it is largely responsible for the AI revolution that we've seen over the last couple of years. I know everybody talks about the funky front end, but there's a lot of back end data stuff that is actually happening to enable some of what is happening on the front end. We'll pick a few sample industries and we'll talk about use cases of time series data across those industries based on our experience. And I'm sure many of you on the webinar, there are some frequent challenges that we run into while trying to implement a modern data ecosystem using time series data. So we'll cover that too. We'll talk about how do we address some of these challenges and prepare for the future. So for the challenges and preparing for the future, we'll do it via a real life use case that I've picked that is relevant to this. And we'll answer any questions at the end. So over the last 2 years or so, we're seeing AI is everywhere. And I wanted to actually take an example of a real world application of time series data. I'm sure everybody is seeing more and more self-driving cars on Australian roads as well as globally. And that's a very good real world example of how there is continuous time series data that is being generated that actually feeds into how the self-driving car actually drives and keeps you safe on the road. So if you look at multiple aspects of how that comes together, you have the real-time sensor data for environmental awareness. So you have sensors that cars typically have. You have LiDAR, radar, etc., and how they continuously map their surroundings and detect objects, pedestrians, etc. So again, that's time series data. The car is doing continuous localization and mapping for accurate positioning, and that's through GPS, etc. And that is required to stay on a planned path. Trajectory prediction and path planning. That's about how do you anticipate future positions of cyclists, nearby vehicles, and again map safe and efficient paths for the vehicle to drive. Machine learning model, historically it is about how do you look at data from previous driving sessions that is responsible for training machines to respond in certain situations in certain pre-planned ways. Number 6, it monitors its own system health and safety to make sure the alerts and the paths and positions it takes are all safe and make sense. And what it is also doing, and it's a real example of edge processing, where all of this is done as close to the edge as possible, which essentially means from a low latency perspective, as close to where the device time series data is actually being measured. So this is quite a complex example of how multiple time series data behind the scenes in terms of vehicle health, driving patterns, all of that is coming together to actually bring us that application of us being able to drive cars, or cars being able to drive themselves. So that brings us to the question: how do you actually define time series data? It's very it's fairly obvious. There's a time series data is a series of data points that are indexed or listed in time order. They don't have to be equal time order. They don't have to be like, for example, every 5 minutes or every 1 minute. They can be in random order, but they still be in a certain time order. Multiple examples, everywhere around us: weather, health, heart rate monitoring, brain monitoring, sales, so on and so forth. So there's actually a lot of time series data in whatever industry you're in that is coming through smart devices and multiple measuring instruments. And time series data is predominantly characterized by 4 characteristics. So you have trends, that is long-term increases, decreases, or stationary movement. So generally, if you look at Australian or Sydney house prices, that's a good example of long-term trending up for multiple years. Seasonality, there are predictable patterns that happen at various points or fixed intervals in the year when certain time series data behaves in certain ways. Cycles are much longer fluctuations without a constant period, longer economic cycles, etc., by using which time series data is affected. And then there's like every good data set that we worked with, there's always some unexplained variability. That's noise. That's part of it, right? So that's typically how you characterize time series data. There are multiple very interesting trends happening in time series data as we speak, right? And we did speak initially about edge computing and real-time analytics. And though in theory, it has been there for quite some time, what is actually happening is some of these edge computing is really happening close to the edge, right? It used to be near real time in the past. It never used to be quite real time, but you're trying to get your insights as close to the device as possible. So without really waiting for your slower pathways of processing visualization, there's a lot of downstream industries that applications are dependent on getting quick insights as close to the edge as possible, and that continues to be the case. But it's become even more because of sensor and device advancements over the last couple of years. The other trend that we've seen is historically, a lot of organizations used to depend on something called as historians, like OSI, for example, right? And we are seeing a trend of where many organizations are moving away from historians, and they're trying to aggregate everything as part of their modern data ecosystem. So they're moving to whatever, if they're on Azure, for example, or AWS, GCP, some of the big, data platforms, Databricks, Snowflake. So they're trying to move away from historians and bring it into their larger data ecosystem. And that's purely because there's been rapid advancement in, the kind of capabilities that some of these platforms are bringing. So they don't want to keep like multiple places where they have data. You have complex event-driven architectures and complex event processing. Again, I'm sure you've seen multiple examples of that, where the architectures, for time series data specifically, it enables real-time responses to specific patterns or conditions. So that's another thing that we're seeing across multiple use cases. Another interesting one is graph neural networks for what we call as spatio-temporal data, right? So whenever a time series includes both time and space relationship, for example, sensor data from various locations, right? So that's an example of graph neural network. So there's a lot of work and adoption of GNNs. And there's a lot of, in terms of the advancement of AI, that has also helped in a lot of synthetic data generation for time series, using GANs, or, you have multiple technologies called, or methods called as VAEs, variational autoencoders, and like, where we're able to generate time series data using some of these new AI capabilities. These are some sample examples of use cases that we are seeing. I've just picked 4 leading industries. By no means is this a comprehensive list, but it's interesting. For example, if you look at energy and utilities, it's a good industry where a lot of work is happening purely because of historically we've had telemetry and then SCADA and then smart devices, and there's all the advancement in devices is leading to a lot of advancement in use cases and analytics on the edge too. So you have predicted asset maintenance around assets, condition of assets, smart metering, multiple, both water and energy utilities are adopting smart meters, and we are seeing that digital metering programs running all over the country, again driven by time series data. Operations on both the water and energy side, demand and load management. On the energy side, with you have solar, etc., becoming a lot more common in Australia, and feeding that back into the grid using what we call DERMS, distributed energy resources management systems. Financial services, another big industry, and they've been doing this quite well for some time. I think financial services is an industry that is fairly mature in the management, primarily because they have to do this for compliance, risk, fraud, anomalies. So they've I think, probably one of the industries that has adopted this very well. Healthcare, we're seeing a lot more adoption in the healthcare industry. Again, that's because of smart devices that are available to monitor, key metrics, and we do that using smartwatches and the wearable health devices ecosystem. And that's being used for both monitoring and diagnosis. On the retail and consumer side, there are again multiple use cases around demand forecasting based on historical time series. You have dynamic pricing is a very good example where, especially in the online commerce world, they're in real time trying to bring prices of competitors together using time series data, and then trying to dynamically price their product to optimize their top line or bottom line. So these are some of the use cases that we've encountered fairly often that have beneath or behind them a large time series data component. Let's talk about a specific use case in terms of what we are seeing in the industry. So I've taken the example of a large water utility in Australia. They want to reduce asset management costs by doing predictive asset maintenance. Again, it's a fairly common use case. We've seen that across multiple water utilities in Australia. And as part of this, they have 4 distinct requirements. They need the ability to be able to visualize real-time data with good performance. And I'm sure many of you who work with time series data in the past know that it's not that easy to be able to visualize multiple years of data very easily on a standard visualization tool, where typically you have performance lags that are happening because of you want to look over 20-30 years of historical data. The second big requirement that they have is they want to be able to do real-time transformations on time series data at scale. And again, if you introduce any kind of transformation into a real-time transformation into the way data goes from data to insights, obviously that introduces latency, right? So the challenge there is to do it really on as close to near real time as possible or real time, so that the transformations do not actually happen and you have insights that are real time or near real time. Number 3 is as part of this problem, you obviously in many cases you have to combine multiple data sources. If it were only looking at operational technology sources, if you're only looking at SCADA, for example, or smart devices, for example, it's relatively easier to build out real-time pipelines and trying to show the data real time. But sometimes there's also use cases where you have to combine, from an asset master, etc. And I have, a few customers who try to do that and still bring it out near real time. And with all of this, with both the volume, velocity, complexity of time series data, you also need to be aware and keep platform costs to a minimum. So that's the case study we'll talk about. And what we'll use this to do is we'll talk through some of the challenges and solutions that this organization and similar organizations go through as part of this case study. So what we've done is we've put this across the data to insights value chain. So you can see from the left-hand side, from data collection and ingestion, to data storage and management, cleaning, pre-processing, visualization, AI, ML, right? So there are a series of challenges that organizations will encounter with time series data across this data to insights value chain. So the first one, volume and velocity, I think that's pretty common. Obviously, time series data, there's you have data coming in milliseconds, and that can lead to huge volumes of data. If you ask me, that is not a really complex challenge, and I think many organizations have solved that with delta lakes and data lakes and everything else. So I think that's I would say that's a lesser of a challenge, right? The second big challenge we see is from a data integration and standardization perspective, because time series data comes from multiple devices, multiple SCADA systems, multiple telemetry systems, multiple kinds of smart devices. And each of these, often have their own type of sensors, own type of logs, own type of transactions, different formats, different time zones, different resolutions. So the integration actually becomes complex, right? How do you even, I know an organization that had like about 6 different types of SCADA systems, each coming with their own formatting, right? So how do you standardize something, the different types of information and send it to the insights? That's a challenge that we'll often encounter. That's a complex problem, right? Time synchronization, because again, time series by definition always doesn't mean it comes in standard intervals. So you have some devices that send data every 10 minutes, every 1 minute, every 1 second, every 5 seconds. But you also have, some SCADA systems that are fairly discrete, so they can, send, every 3 minutes, 6 minutes, sometimes really random, right? So you have to make sure that when you're integrating data from multiple systems, the synchronization is actually possible across these multiple device data. That's on the collection and ingestion side. On the data storage and management, we talked about storage scalability, so I won't really touch that. The efficient data retrieval is again something that we often encounter. And what I mean by that is some of these organizations have up to 100 years worth of historical data, right? So if you're asking, or if somebody runs a query to just query like a 3 weeks worth of data 20 years ago, it actually has to go and kind of scroll through all of that history, and the compute and processing that it actually happens for that is quite high, right? And increases the cost. So how do you set it up such that your data retrieval is most effective? Is again something that we encounter fairly often. Retention and archiving, again, connected to storage. I think that's a problem that has, reasonably been solved. From a cleaning and pre-processing perspective, so because it's time series, there's going to be a lot of missing and anomalous values, right? So and you'll often have, because devices can break, right? You have, whenever devices are malfunctioned, etc., there's going to be huge chunks of data where there's no value coming in or garbage values coming in, right? So they're using the right business rules or right approach to be able to fill in some of those, again, becomes very key to actually derive the right insights. From an outlier detection, time series data is more complex from an outlier detection because certain anomalies typically, right? They could be an actual event of interest, right? So how do you separate out an event of interest from an outlier? That becomes complex. Seasonality and trend, we did speak about, so I'll not speak about that. Visualization, yeah, the way that time series data typically is, it's what we call as there are temporal patterns and trends. And what that means is, because time series data spans multiple time scales, and in terms of line charts or area charts or seasonal decomposition plots, they can become very cluttered with high frequency data, right? So that in turn, the right way to represent becomes complex. And real-time visualization, especially when you're trying to do it on scale or you're trying to visualize specific points in history. The same example, you wanted to look at, let's say, a 4-week or an 8-week or a 6-month window of visualization 20 years ago in data that is spread over 100 years, like, and that becomes very complex. From an AI ML perspective, when you're trying to build, machine learning models on time series data, because autocorrelation and temporal dependencies are because just, it's a time series, right? So observations are sequentially dependent. So the newer time series often depends on what came yesterday or what came before. And because of that, they struggle, traditional ML models struggle with these dependencies and they lead to autocorrelation. So you'll have to use certain specific techniques to deal with these. High dimensionality, because your IoT, in retail, your multiple time series are often simultaneously collected, and it requires what we call as dimensionality reduction, and even your feature selection in AI/ML needs to be very, very well thought out, right? So these are going back to the water retailer, water utility. I think these were some of the challenges that they were dealing with in order to bring for the use cases that we spoke about, right, which are around predictive estimations, operations, and all the good stuff. But underneath data platform, you actually encounter all or most of these issues, right? So how do we actually deal with it, right? How do we actually prepare for the future? So this is how organizations are preparing for the future, right? It's a combination of certain techniques that are being used, as well as certain time series specific technologies that have very time series related features, right? So I've divided it into 9 specific areas. How do you scale data storage, real-time ingestion, all the way to team and process readiness? And I'll not go through each one of those, and we will send you this, for people who have registered. But let's go through a couple of really key ones, right? So from a data storage perspective, we've either seen organizations use what we call as time series optimized databases, and there are plenty in the market, right? And that's not a full exhaustive list. They're also using a lot of cloud native solutions. Sometimes people who don't want to really go for the influx DBs and timescale DBs of the world, they're building out even on cloud native solutions. They're building out solutions for scalability and flexibility. Real-time data ingestion, there's a lot of streaming platforms that do very well, right? From Kafka, Kinesis, event hubs, IoT hubs from an Azure perspective. I think they're really good for real-time ETL. There's a lot of real-time processing frameworks, both in terms of whether they are open source or, for example, Databricks, which uses Spark, and they work very well for transformations. And also there's within Fabric, what used to be called as ADX, right, which is historically before the Fabric changeover. That's really good too. From a low latency querying, again, you optimize queries for specific time series languages, the way you actually partition data for improved query speed. So all of that actually makes a difference. Just going through that list there, from an advanced analytics and machine learning perspective, there's plenty of time series libraries that are specific to time series data, right? So I've put a few layers, Prophet, Glon time series, CATS, and that's specifically for dealing with forecasting and anomaly detection of time series data. If you're doing ML ops, there's, again, some tools that do it really well. TensorFlow is an example, which has a very good option of feature engineering and model management for time series data. Visualization, another key thing that we addressed in the last slide. There are, very time series focused visualization tools, Grafana, Plotly. I've also seen Seek. Seek is some of our utilities customers have it, and that's also for time series data. And from a scalability and cost optimization, again, a lot of organizations, like I said, they don't want to be locked into historians, or they're trying to move away from historians, and they're trying to use cloud first. They're trying to containerize their infrastructure using Kubernetes, etc. They're using tiered storage and auto scaling when required. They're making sure they're tracking usage. And last but not the least, from a team perspective, I think there's some work that is being done to upskill the team in time series data management. There's more focus on working in sandbox environments for continuous improvement and the like. So if you look at just to round off the water utility case study that I was talking about, so they're adopting all of this, right? So, but the question is, building any modern data ecosystem is obviously happens in stages, right? It's an iterative process. So how do you actually, what do you do first? How is real-time ingestion connected to low latency querying, connected to automated data pipelines? What features do you build first? What does a minimum viable product look like? What are features that are necessary now versus necessary later? And I think that the way that we are typically adopting is we are taking a very use case driven approach. And there's a sequence of use cases that need to be built on top of a platform, and we'll build out the platform incrementally with some of these features based on what is the need of the use case. For example, use case one might not need real-time data ingestion, but it still needs scalable data storage. It might need good visualization if it's only descriptive. We'll do that first, and then bring real-time data ingestion as part of step two. So that's pretty much some of our experiences in time series data. Going forward, as AI becomes more and more ubiquitous, you'll actually see that some of this will start coming more and more into the forefront, and these are typically challenges that you will encounter fairly often as you deal with data. That's it. Thank you for listening. Happy to address any questions or thoughts in the chat. Thank you, everyone. Thank you for this listening in, and we will follow up with some content from here, and we look forward to engaging with you. And we'll send out a follow-up email, and if you have further questions, you can also respond to that. But thank you for your time, and have a good day.